Hello. I wanted to take a few minutes and go through some of the calculations that people seem to struggle with on this week's lab. Um, the camera and whiteboard in my classroom aren't very good, so I need to try to do this on my iPad. So please be somewhat patient with me, hopefully. So when you open up your lab, the first set is your relative humidity calculations, and you have a nice little table in Fahrenheit. Okay, we're actually going to do both Fahrenheit and Celsius since we learned how to go from one to the other last week. So we get a question like this. On a warm summer day, the air temperature is 85 degrees and the dew point is 30 degrees Fahrenheit. What is the relative humidity? Well, relative humidity is just simply a ratio of how much water vapor the air actually has versus how much it can hold. So it tells you how moist the air is. So basically, to find relative humidity, I'll figure out how to write. To find relative humidity, we just take, sorry, let me get this on here. We just take our dew point temperature is 30, and if you come over to the table, that means it has 3.54 grams per kilogram of moisture. It's a decimal. And you take that over the air temperature, which at 85 degrees is 26.48 grams per kilogram. So those units will cross out and you get a nice ratio. And 3.54 divided by 26.48 equals, and I get 0.1337-ish, otherwise known as 13.37% relative humidity. So that is nice, dry air. All right. But let's say in the evening that temperature drops and the humidity increases. So what is the dew point? Well, the dew point has probably changed even though the temperature has dropped. So this time it gave us relative humidity. So I'm going to go ahead and write that as a decimal because I think it's easier to do that on the front side. And it is still the amount at the dew point temperature divided by the amount at the air temperature. So we do not have the amount at the dew point temperature. So I'm just going to put an X there for right now. But we do have the air temperature of 65, and we see that the amount 65 degrees is 13.38 grams per kilogram. So now what I'm going to do is cross multiply and divide, but I don't need to divide because it's a 1x. So I'm just going to cross multiply. I'm going to take 0.3946 times my 13.38, and I will get 5.28-ish grams per kilogram. And if I come over to my table, it looks like 5.28 is about 40 degrees Fahrenheit. So that would be my dew point. Oops, I gotta clear this out. Oh, going down to the last question. Says if the humidity is 50.53%, the dew point is 65, what is the air temperature? So now our dew point is 65. We are in a much more humid environment. So again, we would go ahead and put the relative humidity over here, 55.3. Go ahead and change that to the decimal. And the dew point is 65, so it's 65. Again, the air can hold, or the air has 13.38 grams per kilogram. And I want to know how much the air can hold. So I'm going to cross multiply. So I would get 0.5053x equals 13.38. Divide both sides by 0.5053. That gets rid of that. So 13.38 divided by 0.5053 equals, and I get 26.48 grams per kilogram. And if I go to the table, 26.48, that is 85 degrees. So the answer would be 85 degrees Fahrenheit. All right, that gives you one of each kind of example. Clear my drawings. Get out of here so I can scroll down. Now, this table that you're going to have tends to be the more difficult one. So I want to call attention to a couple things. We already did the environmental lapse rate, but be sure and read the question. It's not always 6.5 degrees C. That's an average. It's very much situational depending on where you're at. Sometimes it can be 7, sometimes it can be 8, sometimes it might even be as low as 5. But regardless, that is just the rate that the temperature changes as you go up in the atmosphere. Now, in chapter 4, we added 2 other types of lapse rates. We added the dry adiabatic rate and the wet or moist adiabatic rate, or saturated. So the dry adiabatic rate is usually somewhere around 10 degrees Celsius, but again, that is situational, so please be reading the question for the actual numbers. But dry air just cools more rapidly than moist air. And there are some very good reasons for that you should be reading about in your textbook. Okay. Then once air is saturated, it does not cool as fast or at such a high rate. And so the wet adiabatic rate is usually much lower than the dry. And again, for this particular question, I have it at 5 degrees Celsius per 1,000 meters, but it could be some other number on your lab. So please be reading your question carefully. So here's what we're going to do. We're first going to look at the parcel temperature, and then we will look at the environmental temperature. In determining the stability of air, you need to compare the parcel temperature to its surrounding environmental temperature, and there are some rules in the textbook, and I also gave you another document in the lab. So imagine a partial air that has an air temperature of 23 degrees and a dew point temperature of 13 degrees at the lifting condensation level. So that is when the air temperature and dew point be the same. For you guys in the flight program, I realize that your rule of thumb, whatever the dew point is on the ground, you subtract off about 2 degrees for every 1,000 meters. But this one, I am actually giving you the dew point temperature in the air that it would, like up in elevation, that it would match up at. So that's what I mean by lifting condensation level. So just assume the dew point is 13 degrees. So let's do the partial temperature. The dry adiabatic rate is 10 degrees Celsius. So until we hit the dew point, we're just going to subtract off 10 degrees for every 1,000 meters. Okay. Again, these are rough estimates. It is a always changing temperature. So if we start at 23 and I subtract off 10, that gets me to 13 degrees. All right. Now for the environmental temp, I'm going to subtract off 7 because that's the environmental lapse rate, and that gets me to 16 degrees. All right. At 13 degrees for the parcel, I have now hit my dew point temperature. So instead of subtracting by 10, I will now subtract by 5. And I'm just going to go ahead and keep going up with this one. So I get 8 degrees. And then I get 3 degrees, and then -2, and then a -7 degrees Celsius. So parcel temp's pretty cold up at 5,000 meters. For the environmental temp, that's the easy one. You just subtract off 7 the whole time. So I'm going to have 9 here, and then I'm going to have 2 here, and then I would be at a -5, and I would be at a -12, if I did my math right. Now, on your lab, you'll have another table where you decide if it's stable or unstable, and that is where you look at the temperatures in the columns compared to each other. All right. Then the last question, whoops, I better clear my drawings. And the last question is the little orographic lifting question, or an air mass moving over a mountain. All right, again, I gave you the parameters. The air temperature at the base is 18 degrees Celsius. The dew point at the lifting condensation level is 8 degrees Celsius. And the dry rate is 10, the wet rate is 5. I left that the same as the previous question. I was not that nice to you on the lab, so again, please pay attention to the information in the question. So the first question is, what's the elevation of the cloud base? Well, as long as the air is dry, which it starts at the base is dry, it cools at 10 degrees per 1,000 meters. So if I go up the 1,000 meters, it started at 18 here. So now it is at 8, which is also the dew point. So this is your cloud base. It's also when the air is saturated. So now I will continue to cool, but I will cool at a rate of 5. So now I'm here with 3 degrees at my 2,000 meters. I'm at -2 at 3,000 meters, and a -7, that is some cold air, at 4,000 meters, because I was cooling at the wet rate. Now, as the air mass moves over the mountain, it will deplete itself of moisture, much of the moisture, usually in the form of snow at the upper elevations. So when you come back down the mountain, the air will be dry and it will warm at the dry rate, which would be back to 10 degrees. So from 4 to 3 on the other side, we would simply be at 3 degrees C. And then when we get here, we would be at 13. And when we get here, we would be at 23. And then here we would be at 33. So that'd be some pretty warm air. Now, because it's depleted of its moisture, this area following the mountain would be considered your rain shadow, because that air would be fairly dry and would not pick up moisture again until it collided with some maritime tropical air masses. So I hope this helps. Please start your lab early this week. Please feel free to reach out to me if you have further questions. None of this is that hard mathematically, but it does get a little confusing until you kind of wrap your head around what all these different rates are. Have a great week. If you have any questions, please reach out.